Welcome to DAR Tutors. Today, we're delving into a critical aspect of hypothesis testing. Specifically, we will examine error probabilities and statistical power, fundamental concepts for IB Mathematics AI higher level. In this video, you will learn to, first, you'll be able to define and calculate the probabilities of type 1 and type 2 errors, denoted by alpha and beta. Second, you'll understand the definition and significance of statistical power. And third, you will apply these calculations to various distributions, including normal, binomial, and Poisson, through comprehensive worked examples and IB-style practice questions. Let's begin by clearly defining the two types of errors we can make in hypothesis testing. The first is a type 1 error. A type 1 error occurs when we reject the null hypothesis, H0, when it is actually true. Think of it as a false positive. We conclude there is a significant effect, when in reality there isn't. The probability of making a type 1 error is called the significance level, denoted by the Greek letter alpha. We write this probability as alpha equals p of rejecting H0, given that H0 is true. So, alpha is the significance level of our test. The second is a type 2 error. A type 2 error occurs when we fail to reject the null hypothesis, H0, when it is actually false. This is a false negative. We miss a real effect and conclude there is no significant difference when there actually is one. The probability of making a type 2 error is denoted by the Greek letter beta. We calculate beta as p of retaining H0, given that H0 is false. So, we have alpha for type 1 errors and beta for type 2 errors. These two probabilities are crucial for understanding the reliability and validity of our tests. Now, let's explore the relationship between alpha and beta. They have a dependent inverse relationship. This means they cannot be minimized simultaneously. To understand this, let's look at the graphs of our two distributions. The blue curve is the distribution of the test statistic under the null hypothesis, N0, 1. The red curve is the distribution under a specific alternative hypothesis, centered at some value μ1. Remember, the significance level alpha is the probability of a type 1 error, which is the area under the blue null curve in the critical region. Beta is the probability of a type 2 error, which is the area under the red true curve in the region where we would retain HO. What happens if we decrease alpha? This means we move our critical value further into the tail of the null distribution, making the critical region smaller. While this reduces the area alpha, you can see that the area beta under the red curve must necessarily increase. The inverse relationship is evident. You can't make one smaller without the other getting larger. This presents a compromise in hypothesis testing. In this course, a standard convention is adopted. We fix the significance level alpha, typically at 1%, or 10% before conducting the test. We fix alpha because under the null hypothesis, we know the exact distribution of our test statistic. We don't have this certainty under the alternative hypothesis, which can involve a range of values, making beta harder to control directly. Understanding alpha and beta leads us to our next key concept, statistical power. The power of a hypothesis test is defined as the probability of correctly rejecting the null hypothesis when it is, in fact, false. This is a good thing. We want powerful tests. A powerful test is able to correctly detect a real effect. The formula for power is simply 1 minus beta, where beta is the probability of a type 2 error. So, power equals 1 minus beta. Because beta is the probability of failing to find a real effect, 1 minus beta is the probability of succeeding in finding it. The higher the power, the better the test. We've seen that as beta increases, the power of the test decreases. When would beta be large? Looking at our diagrams again, beta is the area under the red true curve within the retain HO region. If the true mean μ1 is very close to the null mean μ0, the two distributions will overlap significantly. This large overlap will result in a large beta and therefore a low power. It's much harder for a test to detect a small difference that is close to the null hypothesis. This makes intuitive sense. It's difficult to be confident that there's a difference when that difference is very small. A test with low power is likely to miss a small but real effect. Let's put this into practice with a z-test for a population mean. Remember, A z-test is used when the population standard deviation, sigma, is known. Suppose we want to test h naught equals mu naught against the one-tailed alternative. h1. Mu is greater than mu naught using a significance level of alpha. Our goal is to find the probability of a type 2 error beta given a specific true value for mu, which we'll call mu1. First, we find the critical region under the null distribution. Since this is a one-tailed test with the alternative pointing right, the critical region is z greater than z sub alpha. The value z sub alpha is found from the standard normal tables, corresponding to the area alpha in the right tail. Visually, alpha is the area in the right tail of the standard normal distribution, and z sub alpha is the cutoff point for that area. A type 2 error occurs when we retain h naught even though h1 is true. In this right-tailed test, we retain h naught if our calculated z value is not in the critical region, meaning z is less than or equal to z sub alpha. So, beta is the probability of z being less than z sub alpha, given that the true mean is mu1. We must use the true distribution for the test statistic, which is a normal distribution centered at mu1 minus mu naught over the standard error sigma over root n. This gives us our formula. Beta is the probability that our z-score, calculated using the null mean, is less than z sub alpha, where the z-score is actually following the true distribution. Let's work through an example. Cans of chickpeas are labeled 400 Gs. We know the true weight is normally distributed with a standard deviation of 10 G. We want to test if the mean weight is less than 400 Gs. The hypotheses are h naught, mu equals 400, and h1, mu is less than 400. We take a sample of 12 cans and set the significance level alpha to 2%. First, let's find the probability of a type 1 error. This is straightforward. By definition, the probability of a type 1 error is equal to the significance level, alpha, so it's 0.02. Now let's find the probability of a type 2 error, given that the true mean weight is 395 G. This is part A2. We are told the true mean, mu1, is 395 G. First, we need to find the critical value. Since h1 is less than, this is a left-tailed test. We need to find z sub alpha, or more accurately, z sub alpha for alpha equals 0.02. The critical region is z less than some value. We look up 0.02 in our standard normal tables or calculator, which gives us a z-score of negative 2.054. So we reject h naught if z is less than or equal to 2.054. We retain h naught if z is greater than this critical value. Next, we need the true distribution of our test statistic. The mean of this true z distribution is mu1 minus mu naught divided by the standard error. Plugging in our values gives a mean of negative 1732. Finally, we calculate beta. Beta is the probability of retaining h naught, which means the z-score is greater than the critical value given the true distribution. We want to find PZ or 2.054, where z comes from our true n 1.7321 distribution. We can use a calculator for this, which gives us approximately 0.626. So there is a 62.6% chance of making a type 2 error in this scenario. Part B asks for the power of the test. This is simply 1 minus beta. Since we found beta was approximately 0.626, the power of our test is 1 minus 0.626, which is 0.374. This means the test only has a 37.4% chance of correctly detecting the fact that the cans are underweight by 5 grams. This is a relatively low power, suggesting the test isn't very effective. Let's consider another z-test, but this time with a right-tailed alternative hypothesis. In this exercise, we have adult trout. Their length, x, is normally distributed with a known variance of 6. We are testing if the mean length is 27 centimeters against the alternative that it's greater than 27 centimeters using a sample of 9. Part B asks us to calculate beta for a true mean of 29.2 centimeters at 2 different significance levels, 5% and 1%. Let's start with alpha equals 0.05. The process is the same. First, find the critical value. For a right-tailed test at a 5% level, we find the z-score that leaves 5% in the right tail. This value is z sub 0.05, which is 1.645. So, we reject h0 if z is greater than 1.645. Next, the true distribution. The mean of the true z distribution is mu1 minus mu0 over the standard error, which is 29.237, divided by the square root of 6/9, giving a mean of 2.7. Now for beta. We retain h0 if z is less than or equal to our critical value, 1.645. So, beta is the probability that z is less than or equal to 1.645, given that the true mean is 2.7. Using a calculator, this probability is 0.0401. So, for alpha 0.05, beta is about 4%. Now let's repeat this for a significance level of 1%. The critical value changes. For alpha equals 0.01, z sub 0.01 is 2.326. We reject h0 if z is greater than 2.326. The true distribution remains the same, centered at 2.7. Beta is now the probability that z is less than 2.326, given the true mean is 2.7. Calculating this gives 0.354. Notice that when we made alpha smaller, from 0.05 to 0.01, beta became larger, from 0.04 to 0.354. This clearly demonstrates the inverse relationship we discussed earlier. A lower risk of type 1 error means a higher risk of type 2 error. Now, let's look at a two-tailed z-test. In this exercise, we're examining pumpkins, testing h0. Mu equals 6 against h1. Mu is not equal to 6. We have a sample of 15 pumpkins and a 5% significance level. Our goal is to find beta if the true mean is 6.4 kilos. The logic is similar, but the critical region is split into two tails. For a two-tailed test at alpha equals 0.05, we split the area into alpha over 2 in each tail. That's 0.025. The critical values are therefore z0 sub 0.025 and negative z sub 0.25. These values are 1.96 and negative 1.96. We reject h0 if z is less than 1.96 or greater than 1.96. We retain h0 if z is between 1.96 and 1.96. Next, the true distribution. The mean of our true z distribution, with mu1 equal to 6.4, is 6.46 divided by 0.7 over the square root of 15, which is approximately 2.21. Now beta is the probability of retaining h0, given the true distribution. This means we want the probability that z is between 1.96 and 1.96, where z follows a normal distribution centered at 2.21. Using a calculator, this probability is approximately 0.283. So, even in a two-tailed test, the principle is the same. Find the critical region under the null, then calculate the probability of falling within that region under the true distribution. Sometimes, we are given a decision rule in terms of the sample mean, x bar, instead of the z statistic. In example 13, we test h0. Mu equals 42 against h. 1. Mu is greater than 42, with a known variance of 36 and a sample size of 25. The decision rule is to accept h0 if the sample mean x bar is less than 43.5 and reject it if x bar is 43.5 or greater. Part A asks for the type 1 error probability, alpha. Alpha is the probability of rejecting h0 when it's true. The decision rule says to reject h0 if x bar is greater than or equal to 43.5. So we need to calculate this probability under the null hypothesis. The sample mean x bar follows a normal distribution with mean 42 and variance sigma squared over n, which is 36 over 25. Standardizing. This is the same as finding the probability that z is greater than or equal to 1.25. This gives an alpha of approximately 0.106. This means the actual significance level of this test is 10.6%. Part B asks for the type 2 error probability, beta, if the true mean is 44. Beta is the probability of retaining H naught when it's false. The decision rule is to retain H naught if X bar is less than 43.5. We need to calculate this probability under the true distribution, where the true mean is 44. Again, we standardize this probability. The z-score for 43.5 under the true distribution is 43.5 for 44 divided by 6.5, which is negative 5.6, or approximately 833. So we want pz to 0.833, which is 0.202. Notice how the critical value in terms of z is different for calculating alpha and beta. For alpha, we use the null mean. For beta, we use the true mean. The concepts of type 1 and type 2 errors extend beyond z-tests and the normal distribution. Let's look at an example involving the Poisson distribution. In example 14, we test H naught. Lambda equals 2 against H. 1. Lambda is less than 2. We use a sample of 12 values, and the test statistic t is the sum of these 12 values. The decision rule is to reject H naught if t is less than or equal to 16. First, let's find the type 1 error probability, alpha. Alpha is the probability of rejecting H naught when it is true. Under the null hypothesis, each xi is a Poisson random variable with parameter 2. The sum of 12 independent Poisson variables with parameter lambda is itself a Poisson variable with parameter 12 times lambda. So under H naught, t follows a Poisson distribution with mean 12 times 2, which is 24. We need to find the probability that t is less than or equal to 16, given that t is a Poisson 24 variable. Since the Poisson is a discrete distribution, we can use a calculator to find the cumulative probability, p-16, for a Poisson 24 distribution. This gives a result of approximately 0.0563. This means our test has a significance level of about 5.63%. Now let's find the type 2 error probability, beta, if the true mean lambda is 1.5. Beta is the probability of retaining H naught when it is false. The decision rule is to retain H naught if t is greater than 16. We need to calculate this probability under the true distribution, where the true lambda is 1.5. Under this true scenario, t follows a Poisson distribution with mean 12 times 1.5, which is 18. So we need to find pt16 for a Poisson 18 distribution. This is the same as 1 minus pt16. Using a calculator, this probability is 0.6249. This is the probability of a type 2 error. The corresponding power of the test would be 1 minus 0.6249, which is about 0.3751. So you can see that the underlying distribution of the test statistic changes, but the process of finding alpha and beta remains the same. Identify the critical region, then calculate its probability under the null and true distributions respectively. Let's look at one final example, this time involving the binomial distribution. Suppose we want to test if a coin is biased towards tails. The decision rule is to toss the coin 180 times, and if we get 104 or more tails, we accept the coin is biased. Let P be the probability of getting tails. Part A is to define the null and alternative hypotheses, which we have done. Let's move to Part B. Part B asks for the probability of a type 1 error and the significance level. A type 1 error means we reject H naught when it's true. The decision rule tells us to accept H1, which is the same as rejecting H naught if X is 104 or greater. Under the null hypothesis, the coin is fair, so P equals 0.5. The number of tails, X, follows a binomial distribution with n 180 and P 0.5. We need to find the probability that X is 104 or more. Using a binomial cumulative distribution function, Px sus 104 is approximately 0.0219. So the significance level of this test is about 2.9%. Now for Part C. Suppose the coin is actually biased with a probability of tails, P, equal to 0.65. We need to find the probability of a type 2 error and the power. A type 2 error means we retain H0 when it's false. The decision rule is to retain H0 if x is less than 104. We need to find this probability under the true scenario. Under the true scenario, x follows a binomial distribution with n palkitki and 180 palkitki and p 0.65. We need to find the probability that x is less than 104. This is the cumulative probability Pt dx equals 103. Using a binomial calculator, this is approximately 0.0184. This is the probability of a type 2 error. It's quite small in this case. The power of the test is 1 minus beta, which is 1 minus 0.0184. This gives a power of 0.9816, or about 98.16%. This is a very high power, which is excellent. It means this test is very likely to detect a genuine bias towards tails if the probability is 0.65. Before we move to practice questions, here's a brief but important call to action. For expert tuition in IB A-Level and IGCSE curricula, contact DAR Tutors. You can find our contact information at dartutors.com. Our expert educators are here to provide the personalized support you need to excel. Let's consolidate our understanding with some IB-style practice questions. Question 1 involves an aged care office. The number of calls received per 5-minute interval, X, follows a Poisson distribution with mean lambda. A receptionist should be hired if the mean rate exceeds 2 calls per 5 minutes. Over a particular 1-hour interval, 29 calls were received. Conduct a hypothesis test at a 1% significance level to determine if a new receptionist should be hired. Here's the solution for question 1. The null hypothesis is that the mean rate is 2, so H0, lambda equals 2. The alternative is that the rate has increased, so H1, lambda is greater than 2. The test statistic for the 12 5-minute intervals, the total number of calls T, will be Poisson 12 times lambda. So, under the null hypothesis, T follows a Poisson distribution with mean 24. We want to find the p-value for our observed value of 29 calls. The p-value is the probability of observing a result as extreme or more extreme than our sample, assuming H0 is true. So we need pt greater than or equal to 29. For a discrete distribution, this is 1 minus the cumulative probability pt less than or equal to 28. Using a calculator, this is 1 minus 0.8656, which gives a p-value of 0.1344. Finally, we make our decision. The p-value of 0.13444 is greater than our significance level alpha of 0.01. Therefore, we fail to reject H0. There is insufficient evidence at the 1% level to conclude that the call rate has increased. Question 2 is about a coin that may be biased. Eri believes her coin is fair, so the probability of a head, P, is 0.5. Her friend Mayuki thinks it's biased, with P greater than 0.5. To find out, Eri tosses the coin 12 times and rejects her belief, rejects H0, if she gets 10 or more heads. Part A asks for the type 1 error probability and significance level. A type 1 error is rejecting H0 when P 0.5. Based on the decision rule, this means finding the probability of getting 10 or more heads in 12 tosses of a fair coin. X follows a binomial distribution P12 0.5. P count 10 is the sum of the probabilities for X or 10, 11, and 12. You can calculate these manually using the binomial probability formula or use a binomial cumulative distribution function on your calculator to find 1 minus px e to 9. The result is approximately 0.093. So, the type 1 error probability and significance level are both about 1.93%. Part B asks for the type 2 error probability and power if the true probability of heads is 0.6. A type 2 error is retaining H0 when P is 0.6. The decision rule says to retain H0 if x is less than 10. Now x follows a binomial distribution b to 12, 0.6. We need to find the probability of x being less than or equal to 9. Using a calculator, this cumulative probability is approximately 0.9168. So the probability of a type 2 error is about 91.68%. This is a very high probability, meaning the test is not effective at detecting a coin with this specific bias. The power of the test is 1 minus beta. 1 minus 0.9168 gives a power of only 0.00832, or 8.32%. This extremely low power means ARRI has a very small chance of correctly concluding that the coin is biased when P 0.6. The sample size of 12 tosses is likely too small for a powerful test. Our third practice question involves the weight of chickpea cans from the first example. We are testing H0. MU equals 400 against H1. MU is not equal to 400. We have a standard deviation of 10 and a sample of 16 cans. H0 is rejected if the sample mean is less than 398 or greater than 402. Part A asks to show the significance level is approximately 0.05199. Alpha is the probability of rejecting H0 when it's true. The decision rule defines the rejection region for X bar. Under H0, X bar is normally distributed with mean 400 and standard error 10 over the square root of 16, which is 2.5. We standardize the critical values 398 and 402, giving z-scores of 0.8 and 0.8. So alpha is the probability that z is less than 0.8 or greater than 0.8. By symmetry, this is 2 times the probability of z being greater than 0.8. P in 0.8 is approximately 0.21199. 2 times that is 0.4238. This is not 0.0519. There might be a typo in the original question's target value. Let's assume the question meant for the decision rule to be X bar less than or equal to 395 or X bar greater than or equal to 405. In that case, the z-scores would be plus or minus 2, and alpha would be 0.0456. To get 0.0519, the critical z-scores would need to be around plus or minus 1.94, which corresponds to sample means of 395.15 and 404.85. We'll proceed with the given decision rule and acknowledge the discrepancy in the expected result. For the given decision rule, alpha is approximately 0.4238. Part B asks for the type 2 error probability if the true mean is 398.4 grams. Beta is the probability of retaining H0 when the true mean is 398.4. Retaining H0 means X bar is between 398 and 402. We need to find this probability under the true distribution, where X bar is normally distributed with mean 398.4 and standard error 2.9. Standardizing the critical values under this true distribution gives z-scores of 0.1 and 1.4. We want to find the area between these. A PASA 144 is 0.9251 and PZ016 is 0.4364. Subtracting them gives beta approximately 0.4887. Question 4 is about a claim by an advertisement. It says that 20% of households use Ongodo washing powder. A statistician recommends sampling 100 households. The advertisement's claim is only considered reasonable if 13 or more households in the sample use Ongodo. The null hypothesis is that the proportion P is 0.2. The alternative hypothesis, if the claim is to be challenged as not reasonable, would be that the true proportion is less than 0.2. The test statistic X, the number of households using the powder, follows a binomial distribution B1100P. Part B asks for the significance level of this test. Alpha is the probability of rejecting H0 when it's true. According to the decision rule, we reject H0 if X is less than 13. Under H0, X follows a binomial distribution BTB1100 0.2. We need to find PX, 13, which is the cumulative probability Pt is equals 12. Using a binomial calculator, this is approximately 0.0069, so the significance level of this test is very low, about 0.69%. Part C asks for the power of the test if the true proportion is 17.5%. The power is 1 minus beta. Beta is the probability of retaining H naught when the true proportion is 0.175. We retain H naught if x is 13 or greater, so we need to find PTR 13 for a binomial distribution B 100, 0.175. This is 1 minus ppx equals 12, which is 1 minus 0.3015, giving a beta of 0.6985. The power is 1 minus beta, which is 1 minus 0.6985, giving a power of 0.3015. So, for a true proportion of 17.5%, the test only has about a 30% chance of correctly concluding that the advertisement is misleading. Finally, question 5 revisits the fizzy drink machine. The volume Y is normally distributed with mean mu and standard deviation 2. We test H naught. Mu equals 330 against the two-tailed alternative to H1. Mu is not 330. A sample of 16 cans is taken. The machine is accepted if the sample mean Y bar is between 329 and 331. Otherwise, it's rejected. Part A asks for the significance level alpha. This is the probability of rejecting H naught when it's true. The standard error is sigma divided by root n, which is 2 over 4, or 0.5. Under H naught, the sample mean Y bar follows a normal distribution n 330 0.5 squared. We find the z-scores for our critical values. Z equals 329 to 330 0.5 equal 2, and z equals 331 to 330 key 0.552. So alpha is the probability that z is less than or equal to 2 or greater than or equal to 2. This is 2 times p azid equals 2, which is 2 times 0.0228 or 0.0456. So the test has a significance level of 4.56%. Part B asks for the type error probability if the true mean is 328. Beta is the probability of accepting H naught when the true mean is 328. Accepting H naught means the sample mean is between 329 and 331. We calculate this probability under the true distribution, where Y bar is normally distributed n 328, 0.5 squared. The z-scores are 329 to 328, 0.5, x2, and 331, 328, 0.5 yield 6. We want the probability that z is between 2 and 6. This is pzd6 minus pz2, which is approximately 1 minus 0.9772, or 0.0228. This is a fairly low beta, meaning the test has high power to detect a true mean of 328. That completes our in-depth look at error probabilities and statistical power. We have defined type 1 and type 2 errors, alpha and beta, and explored their inverse relationship. We've seen that power is 1 minus beta, and how it represents a test's ability to detect a true effect. Through various examples from the IB/AI/HL curriculum, we've applied these concepts to z-tests and tests involving the Poisson and binomial distributions. Understanding these error probabilities is crucial for interpreting the results of any hypothesis test correctly. We've met our learning objectives for this video. You can now define and calculate alpha and beta, understand the meaning of statistical power, and apply these calculations to different distributions. Keep practicing these types of problems to build your confidence and mastery. Thank you for watching.